All right, thank you. Yeah, thank you everyone for coming along to the talk. My name is Matt Cousins, and I work as an academic ecosystem development manager at Arm. So I'm going to be talking about how Arm is building the future of AI compute, and we'll sort of look at both cloud and then moving pretty quickly from cloud to the edge, and talking a little bit about physical motion as well. So I will briefly start with a little bit about who are Arm and what do we do, because although I'm sure that most people, if not everyone on this call, is familiar with Arm, there are sometimes a few misconceptions and also some things have changed in our focus over the years, and of course we've got new kind of hardware IP. I'll then pretty quickly move on to some key trends in AI adoption, and look at some of the key optimization techniques and tools used for getting AI onto different hardware, and essentially assess how these trends, these optimization techniques and these tools influence and enable the use of different hardware for different AI use cases. So I'll look at CPU for the cloud and the edge, and then CPU of a sort of microcontroller class for embedded systems and how you might want to pair that with neural processing units for machine learning. And then I'll also touch on some of our kind of mobile GPUs that are coming with embedded neural accelerators, which we announced last year. And then I'll provide a bit of information about Arm's resources for educating the next generation of AI fluent hardware and software engineers. And I'll touch on the routes for educators and academics, and then also some routes for students that you may wish to share with your students. So brief history of Arm: started in 1990, joint venture between Acorn Computers and Apple and VLSI Technology. And from 1993 onwards, it was designed into the first mobile phones and then smartphones. So this is CPU IP. And Arm was sort of traditionally known for having an advantage in that it's a reduced instruction set computer architecture, which of course typically means low power, good power efficiency, and the capability of sort of small form factor and being able to fit into these small mobile phones and embedded devices whilst preserving battery life and giving good thermal performance. But this advantage, it spread to more than just phones. It spread to embedded systems and IoT devices, and also increasingly at the cloud as well, because particularly at scale, having small power efficiencies can be very useful, both in terms of the total cost of ownership, running these devices and powering them, but also in terms of logistics, keeping them cool, having to water cool data centers, and then considerations for the environment as well about the amount of power that is used. So as I mentioned, it was a 1990 Cambridge startup, famously in a turkey barn, which you can see on the left in Fulbourn. But if we now move to 35 years in the future, it has a global market capitalization of over 100 billion US dollars. It's the UK's most successful tech company, and we've been able to upgrade our offices somewhat from the turkey barn on the left to the sort of thing you can see on the right. And actually, this is where my team works, specifically on that floor there. So we have over 8,000 people working at Arm, and 80% of which are engineers from 91 different nationalities. And we have offices in 28 different sites across 16 different countries. So there's a lot of opportunities for your students to get involved for their career and for student projects whilst they're at university as well. But what do we actually do? Well, we provide the IP that silicon partners then take and integrate into chips that they tape out, and then those chips go into products across sort of 5 main markets. So as I've mentioned, Arm's traditionally been associated with mobile phones, Internet of Things, and embedded systems, but actually it's also always had a strong presence in the automotive market as well, again for the same reasons and advantages like power efficiency, form factor, and the fact that the ecosystem is very broad and used by a wide range of partners. So software developed for one ARM-based chip is very easy to get running on another ARM-based chip. And increasingly, ARM devices are being used in the sort of PC and notebook tablet market with things like Windows on ARM or Apple Silicon. And as I mentioned as well, increasingly, ARM is becoming the foundation of a lot of cloud-based infrastructure and on-premises sort of data center and server infrastructure as well. So now in many public clouds, ARM Neoverse IP is used as the kind of CPU foundation, whether it's AWS, Google Cloud, Microsoft Azure, or over in Asia, Tencent Cloud. Many of these are using ARM Neoverse as a foundation for their clouds. And these CPUs are actually capable of running AI and machine learning. And I guess essentially a big takeaway from this presentation will be thinking about other hardware beyond your typical use of GPU for AI and how that hardware can be used when appropriate optimizations and tools are used for AI. So what is the kind of key IP that we're providing at the moment? Well, Cortex-A is one of our kind of most well-known pieces of IP. This is a CPU and is intended as an application processor. So this is capable of running a rich operating system like Linux or Windows on ARM. And you'll find these devices in anything from a Raspberry Pi to a mobile phone. And some mobile phones will have a variant of Cortex-A called Cortex-X as well, which is essentially a more premium and higher quality version. The Cortex-R is then aiming at sort of real-time processors. So any use cases, whether it be automotive or other safety critical use cases where you need real-time determinism, that would be where the Cortex-R would fit in. And then something that you're probably very familiar with is the Cortex-M, which is our microcontroller class processor. And this is used typically in bare metal situations or where you may want to use an RTOS. And you need that deterministic behavior, but also it's very important to have power efficiency and small form factor as well. And you perhaps don't need as many features as you might have on a Cortex-A. And then I've mentioned Neoverse, which forms the foundation of infrastructure and cloud processors. And this is used very widely. But something that you may not be familiar with is our Ethos-U neural processing unit. So ARM doesn't just do CPUs. We also make neural processing units. And these are typically used at the embedded and edge type use cases. So perhaps you have a microcontroller class device like a Cortex-M, or you may have a Cortex-A that's been specifically geared towards an edge and embedded use case, but you want to bring some machine learning to that use case. You could use the Cortex-M, and there are some features that I will discuss about how you could use the Cortex-M, and you could use the Cortex-A, which also has its own architectural features that would enable that. But if you want to bring significant machine learning compute to the edge, then your Ethos-U neural processor would be the way to go. And then finally, ARM is also in the business of producing IP for graphical processors, and we have a Mali and Immortalis range, which are typically found in mobile devices. But we found that partners obviously can have a difficult time integrating all of their IP into a system on chip. What we've done in the past is essentially provide the ingredients and then support the partners with putting those ingredients together to create a chip and then tape it out. But this can be very difficult. So what we've started doing is providing compute subsystems. So these are essentially the ingredients and the recipe. We provide a pre-configured, validated, and optimized solution where we've essentially pieced together some bits of IP, ensured that they work together well, and then we provide that as a single sort of piece of IP to our partners, and that enables them to go from design to final chip a lot faster and a lot easier. And the main compute subsystems fit into the kind of vertical markets that I mentioned earlier. You've got Neva for client, focusing on PC and laptop. You've got Neoverse for infrastructure, Xena for automotive, Orbis for the Internet of Things, and Lumex for mobile devices. So now I'm going to move on to where are we at today with AI applications from the cloud to the edge and in physical motion, and essentially share how AI can run not just on a GPU or a TPU, but also on CPU and of course NPUs as well, and the appropriate times to use them. But first, a key trend in AI that sort of sets the scene for why we would want to and why we're able to do this. So AI adoption going forwards is all about inferencing. So AI training is very expensive, and this is what we typically hear about. We hear about training AI models like GPT-4, GPT-5, and this would be run on GPUs or TPUs, which is tensor processing units, essentially AI accelerators. But this is really only the tip of the iceberg. This accounts for around 15 to 20% of total AI workloads, whereas going forwards, the growth in AI is actually going to be in inference, with 80 to around 85% of total AI workloads expected to be in inference. So inference is when you actually have a trained model and then you want to run the model and get an output from it. And it's quite obvious to see that once models have been trained and they're reasonably effective, and then they're deployed for users in applications like ChatGPT or Claude, that then actually the use of AI starts to shift from kind of preparing the models to their application. And it's not just end user applications, but also automated systems that will leverage the output of these systems and be constantly prompting for new results. So we need to start to consider inference, and we are able to consider alternative hardware options to your GPU and your TPU, because training is very intensive and requires essentially workhorse devices. But inference can be just a single inference to get a result and provide it back to you. And it doesn't have to have that training feedback loop for many, many hours that training an AI model requires. So actually, it can be faster and more efficient in many situations to use CPUs as opposed to GPUs. So as I mentioned at the start, these are the kind of key areas that I'm going to look at. I'm going to look at the kind of Cortex-A and Neoverse class of processor, so at the cloud and at the edge, and how we would optimize and why we would optimize for that CPU. I'll look at the microcontroller class and how you may want to augment that with a neural processing unit. And then I'll also mention our new and interesting application for AI enhanced graphics for mobile gaming with neural accelerators embedded into GPUs. So why would we optimize for CPU inference? So I've mentioned that traditionally you would use a GPU and a TPU for training, and you could easily argue, okay, inference is the future, but why not continue using GPUs and TPUs? They are workhorses, they are designed for it, and they are the most powerful. Well, a key factor here is cost efficiency and ubiquity and picking the right tool for the task. You don't need to use something that has been designed for training and is far more powerful than you need if you don't need it. And then the other factor is if we want to bring machine learning to the edge and to embedded systems, we have to think about the availability of hardware. So CPUs are already ubiquitous. Any device that has any form of general purpose compute has to have a CPU at minimum, but many devices, particularly in embedded systems, will not have a GPU or a specialized accelerator because there was simply no need. And there's also going to be pushback against putting specialized accelerators and GPUs into these devices because, again, there has to be a question about whether it's needed, and there has to be a justification before the cost of implementing a GPU or specialized accelerator is taken. And there also needs to be consideration again about the power factor. GPUs and TPUs are power hungry, and therefore they simply aren't appropriate quite often in embedded systems. So we can leverage existing devices and the CPUs in them to perform inference at the edge, and we then don't contribute to e-waste by having to replace these devices. We can make use of what's already there. And then latency is another factor. Even if on device you did have an accelerator or a GPU in an embedded system, there is a latency cost incurred by the CPU orchestrating that GPU or TPU to perform an AI workload and then get the result back. And that latency cost could be critical in a real-time situation, and therefore could be not ideal for the application, to say the least. There is also then the option of saying, well, I won't have an accelerator or a GPU in my embedded system, but I will connect it to the cloud and make use of accelerators in the cloud. But again, you have a latency issue where you have to send data to the cloud and receive back from the cloud. And then also you have the issue where you actually require some form of cloud or network connectivity to do that, and that's not always possible. Additionally, if you were to use the cloud or network to on-premises infrastructure, then you are transmitting data away from the local device. And of course, there are issues there with data security and privacy and regulation issues. So keeping users' data on device where possible is always preferable. Okay, so I've said that there are some reasons why we might want to optimize for CPU inference, but is it actually possible? And yes, it is. So we can leverage the Arm architectural features to ensure that we have optimal inference on CPU. And one of those main features has been on CPUs for a long time, and that's single instruction multiple data, or SIMD, which performs the same operation on multiple data elements concurrently, which increases throughput for matrix multiplication. Of course, matrix multiplication is the foundation of a lot of AI models, and therefore this is very effective. So Neon has been present on Arm devices for many years and was the initial implementation of this single instruction multiple data. And Helium is essentially the equivalent for microcontroller class Arm devices. But more recently, this has been extended. So Neon has been extended to the scalable vector extension, which essentially further increases the vectorization and the throughput and takes it from a 128-bit register scalable all the way up to 2048. So you can get a lot more vector operations happening in parallel. Another feature is the integer 8 matrix multiplication architectural extension. This is implemented as an instruction in the ARM architecture called SMMLA, and essentially enables 8-bit integer matrix multiplication, which again, of course, this is vital for the foundation of many AI models and allows this to be accelerated directly in hardware. And then most recently, we have the scalable matrix extension, which has been specifically developed for matrix multiplication operations and essentially extends the scalable vector extension. And this uses the outer product method for matrix computation because this is essentially most efficient and most optimal for using cache. It ensures that the elements used for computing the matrix will appear in cache at the same time, and then those elements are used rather than opting for a different approach that would result in many more refreshes of the cache. And we're able to demonstrate significant performance increase by using the scalable matrix extension. So this is comparing with the traditional Neon approach for two different models, a 1 billion parameter and a 3 billion parameter Llama 3.2 model. And it looks at the input token stage, which is the prefill stage for large language models, the output token stage, the decode stage, and then it compares the overall. And you can see that actually this gives something away about how large language models work. At the prefill input stage, there's a lot more dependency on matrix multiplication, and it's able to be parallelized a lot more than at the decode stage. So you can see a much greater speed up, around 16.7 times and 19.4 times on the respective models at the prefill stage, whereas it's quite a bit smaller of a speed up at the decode stage. But the overall is still a significant around 3 times speed up on tokens per second when using the scalable matrix extension. Now, it's all well and good knowing that the hardware has these features in them, but a typical software engineer is writing code in Python, perhaps using a framework like PyTorch or TensorFlow, and they aren't necessarily thinking about what features their hardware has. And in all likelihood, they're writing software that will run across multiple different pieces of hardware that will have varying architectural extensions and capabilities. So they're not going to be thinking with a particular piece of hardware in mind. So how are they able to leverage it? Well, Arm KleidiAI is essentially a library of optimized AI microkernels, and these microkernels will leverage the available hardware in the best way. So whatever extensions it can see on the device that the software is running on, it will utilize a microkernel to take advantage of that. And the key thing is that this is transparent to any machine learning engineer that's using the framework. This is built into typical mainstream frameworks like PyTorch and TensorFlow, and you simply don't need to worry about it. If you're using a mainstream framework and you're running on an ARM-based device, then KleidiAI will automatically ensure that the appropriate extensions and hardware acceleration is being leveraged in the best way. And this is an example using PyTorch. So you can see essentially you've got your model at the top, and you would be using the PyTorch framework. And there are various libraries that comprise PyTorch. And right down towards the hardware, these will leverage the Arm Compute library for traditional machine learning use cases and the Arm KleidiAI library for generative AI use cases. And then these in turn will ensure that the correct hardware features, whether it's Neon or SVE or SME2 or the i8mm extension, are leveraged to ensure that you can run your AI model effectively on a CPU. So how else do we optimize for CPU inference? Because we've only covered part of the issue. And one of the things that helps is the trend towards smaller and more specialized models. So Sam Altman, CEO of OpenAI, has actually said that the era of large models is over, and the focus now is on specializing and customizing the models and essentially training them on domain-specific data. I think this is probably intuitive to everyone, that you could have a very large model like GPT-5 that is trained on a wide variety of topics and is very good at all of those topics. But you could actually just train something specifically on healthcare or specifically on finance or specifically on software development, and it can be very good at that one application, know absolutely nothing about the other applications, but it doesn't need to, and that way the model can be significantly smaller. And that shouldn't really be a surprise to anyone. And of course, you can see in these sorts of results, an example here in finance. So FinGPT, only a 13 billion parameter model, is achieving the same or better than these generalized models like GPT-4. And we don't know exactly how many parameters are used for GPT-4, but it's widely understood to be in the hundreds of billions of parameter mark. So 13 billion is significantly smaller. And because we're able to use these specialized models, and they are far much smaller, but also in their particular domains, they have incredible quality, then we're able to run these on CPUs a lot easier because they have a much smaller memory and compute footprint. There is then a further optimization we can do to these models to make them even better for CPUs, particularly at the edge, and that is quantization. So we have a particular size of model, but we can choose how we actually represent the data in what format. So higher precision floating point 32 representation of the data is typically preferred for training, but actually you can use a much lower precision when you come to inferencing. So the higher precision format is used to ensure that the training done is very accurate. But actually, when you use a lower precision format, perhaps even looking at integer formats like int8 and int4, then the accuracy typically only decreases by around 1%. But at the same time, your model is 3 times smaller and 2 times faster because it significantly decreases your memory and compute footprint. So it's much better for a CPU. And in most situations, 99% of the quality is going to be more than sufficient. There obviously could be some situations where you have a critical need for it to be as accurate as possible. But in the vast majority of applications, this small trade-off is not a problem at all. So this is a quick demo. Essentially shows on the left someone using PyTorch, and although KleidiAI is integrated into PyTorch, for this demo we've ensured that it was not leveraged. And then also the user on the left has not quantized their model, and they've stuck with floating point 32. So you can see it's a lot slower on the left. They've not used KleidiAI and they've not quantized their model. They have used a low parameter model, so it's appropriate for running on a CPU, but it's essentially a lot slower than it otherwise could be. Whereas on the right, they have used KleidiAI, so it is now leveraging the hardware appropriately, and they have quantized it down to int4 representation. And there is a significant speed up, and now the user on the right is able to execute another prompt and do another inference far sooner than the one on the left. And this is actually running on a Neoverse-based cloud processor, part of AWS. And you can try out this demo for yourself at the link at the bottom of the page. So you're more than welcome to take a screenshot or something at that link if you want to get hands-on and try out that demo yourself. You might ask about edge-specific runtimes. Some of you may have heard about Executorch and LiteRT. So these are the edge-specific runtimes for PyTorch and TensorFlow, respectively. They're essentially portable, lightweight packages with no extra dependencies or bloat, and they essentially provide a minimal production-grade inference runtime. And these can be used on edge devices like Raspberry Pis. They can be used on microcontrollers, or they can even be used on mobile phones. And on CPUs in particular, they will also leverage KleidiAI. So Executorch and LiteRT, they optimize inference on Cortex-A CPUs via XNNPAC, which then leverages KleidiAI. And they're also capable of deploying to ethos-U NPUs as well. So you are fully able to use the edge-specific runtimes on ARM devices as well, again, for even better performance at the edge, and now enabling you to even further use CPUs or other devices that aren't your typical heavy GPU. So now moving on to the really kind of like embedded side of things, and starting with microcontrollers. What are you currently capable of doing with AI on the edge? So Cortex M55 and Cortex M85, these come packaged with Helium. Now, Helium, as I mentioned earlier, is essentially the microcontroller equivalent of Neon, so it allows some SIMD instructions. And this allows you to kind of get away with doing some image classification, facial recognition, and keyword spotting. You could then upgrade slightly and use a Cortex A320, which is essentially a Cortex A that has been gauged for embedded use cases. But this doesn't provide you too much additional capability, though you do now have access to Neon and SVE2. But if you really want to make full use of machine learning in embedded situations, then the correct approach would be to start considering using an NPU. These allow you to do applications like collaborative robots and real-time audio processing. And if you're using the high-end NPU, which has full transformer support, you can actually run small language models at the edge as well. And I'll show you a little demo video of that. And these NPUs, they pair up with either a Cortex-A or a Cortex-M. So there are many different solutions in the market that make use of them at the kind of microcontroller level or the more sort of typical edge device level. If you're going to use the NPU, then there are some kind of key tools that you need to know about, and you need to know about TOSA, which is the tensor operator set architecture. So this is around 70 operators that work on tensors, independent of any software or hardware design. And these operators are essentially the compliant, acceptable operators to run on the NPU. So essentially they are machine learning operations that could be accelerated in hardware. And the different NPUs will support some number of these operators. So the first thing to do is use the TOSA checker tool. So you would essentially check your model and check that it's TOSA compliant, because it can't have any operators that aren't part of the TOSA specification. If you do have an issue and your model has something that is non-TOSA compliant, you can use the TOSA adapter for Google's Model Explorer to actually look inside the model and analyze the different layers and operators and essentially find out what the issue is. And then you can pick a different model, or you can adapt your model to fit the TOSA specification. And then finally, you can compile the model so that it essentially delegates as many operators as it can to the NPU. And any operators that aren't supported by the NPU, it will then fall back to the CPU. And this is all provided by Arm to provide a seamless kind of route to deploying your AI models quite simply onto the EthosU NPU. So this is a bit of an overview of how the Vela compiler works. You would provide either a TensorFlow Lite or TOSA file at the input. And it simply just checks, is this TOSA operator supported by the available hardware? If it is, it will optimize it and run it on the NPU. And if it isn't, then it will fall back to the CPU. And the same operation will be implemented as a sum of multiple CPU instructions. And obviously, the ideal situation is that your model, you've looked inside it with Model Explorer, and you haven't just confirmed that it's TOSA compliant, but you've also tried to ensure that it uses operators that are supported by the hardware that you're targeting, because as much as you can optimize as possible is the better. And then this is a bit of an example of Cortex-A53, which is the sort of CPU you could expect in a Raspberry Pi 3B versus the EthosU65. And we can clearly see that compared with a CPU, from a few years ago, using this NPU, as you would expect, it has a significant performance increase of around 12 times. And you would expect that because that's what this NPU is designed for, and this has been benchmarked on a convolutional neural network that's typical kind of embedded use case. But what you might not expect is the power efficiency, because typically if you're using a GPU or a TPU, it's understood that you're going to have great performance, but it's not going to be very power efficient. Whereas using this NPU actually has around 90 times the power efficiency, because this is designed to optimally accelerate these operators. And then this is a demonstration of actually running a small language model on the EthosU85, which is the latest neural processing unit. And this is actually back when it was being prototyped on an FPGA platform. And it's able to achieve around 8 tokens per second, which is more than sufficient for reading speed. And of course, if you opted for a higher configuration of multiply accumulate units on this EthosU, and you opted for higher clock frequencies, then you could get even higher performance. And I'll show a video in a second as well of our intern Josh, who used a bit of hardware from one of our silicon partners who took the EthosU55 and provided a bit of kit that is more than capable of doing real-time object detection and pose recognition. And you can see here it's able to track him as he moves his arms. And this is running on a power bank. When I get the message across that this is very power efficient and enables you to do this real-time detection and tracking at the edge, this is not plugged into a wall. It's more than capable of just running off a USB power bank. And now I will just briefly talk about neural graphics technology, which is essentially bringing generative AI to graphics technology, mobile GPUs. So this concept is essentially using generative AI to render around 75% or reconstruct around 75% of pixels, whilst only rendering using the graphics pipeline around 25%. And essentially using AI to reconstruct the 75% is significantly easier, particularly if it's using one of the embedded neural accelerators in the new GPUs that are coming out soon, than it is to use the graphics pipeline to generate the whole set of pixels. And we're able to show that the result is actually mathematically of the same image quality when using generative AI, whereas the performance, of course, is expected to be significantly better because we're freeing up a lot of graphics pipeline to work on other things, reducing its workloads at maybe around 25%. So you can see on the left, not using generative AI, and then on the right, the image is identical, and yet the GPU has a lot less work to do.